And along with myself from Echometer, we have Gustavo Fernandez, who will be manning the chat and assisting with the Q&A session. You see Ken Skinner, Dieter Becker, and Dr. Tony Podio, and Lynn Rowland, who will be presenting today. Today's session is titled Using Acoustic Fluid Levels to Analyze and Troubleshoot Gas Wells. So Lynn, I will go ahead and turn it over to you now.
All right, well, good afternoon, everyone. This is our 7th Ask Echometer session, and the presentation, Carrie already said the title, and we're going to have probably about 9 examples at the end of the Q&A session to show different features about that go along with the presentations on shooting fluid levels on gas wells. It looks like here I misspelled application, put a B instead of an S, looks like. But anyway, this is a paper that we wrote in 2006 that talks about several different wells we shot fluid levels on and depressed the fluid levels in gas wells, and we were working on the gradient and how to determine the gradient. This is another paper that we published in SPE, and it talked more about liquid loading and critical rate and different types of gas wells. And this paper I was a co-author on with Rob Sutton and Jim Lee. And let me see if I can pull that one up and just show you a picture out of it, because I've got it loaded right here, I think. Yeah. And so this is a SP paper, and it talks about where you use the critical rate and whether you apply a critical rate at the surface, calculation at the surface or the bottom of the well. And if you were to look at this graph right here, it says if the wellhead pressure is fairly high and the temperature gradient is fairly warm versus depth, then you'd use the wellhead. And then if the wellhead pressure is low and the temperature gradient is not very high, then you'd use your calculations at downhole. And this is a pretty good paper that discusses a lot of the calculations and equations in critical rate. And then we'll have a spreadsheet that you can download that has the critical rate calculations for Turner, and also a PDF that shows a plot of critical rate versus tubing size versus gas rate. And it's at the pressure and surface flow rate of the well. So no, it's actually at this pressure, the flow rate of the pressure of the well. So anyway, this is a good example that a good paper to reference if you're interested in. I want to thank Carrie Ann and Gustavo for helping on this presentation. And if you don't have TAM on your computer, you can access our webpage under software and total asset monitor, and you can download the TAM software that you can then import the examples into when we talk about the examples at the end of the class. Now, when prior to 2000, I didn't really work a lot with gas wells. Most of the wells I worked with were rod pumping or wells with pumps onshore, typically, and we shot fluid levels down the casing annulus to determine pump intake pressure. And it was a pretty simple test that we did, and we were, as a company, I work for Emerald Hess, we're pretty happy with using that acoustic fluid levels on producing wells. When I came to work for Echometer in 2000, we went to a few wells that were gas wells and started shooting fluid levels down the tubing, and it was, to me, it was a new adventure. And probably the first thing that was surprising to me was I could see the tubing collar recesses on the inside of the tubing. And then I realized that you could count the tubing collar recesses shooting down the tubing just like you can count the collars on the outside. It's easier when the pressure's high. It's easier when the well's not noisy to shoot down the tubing, but it's a pretty effective tool. And we looked at quite a few wells that were sometimes plunger lifts, sometimes just gas wells that had liquid loading problems, and we realized that we could see the the height of the liquid level in the tubing, and that represented the back pressure in the formation when it was loaded flowing below the critical gas rate to get the velocity to carry the liquid out of the well. And so that became kind of an interest to me to start to do studies on that. And so we started working on fluid levels in gas wells and into plunger lift. And so the advantage of doing this, of using an acoustic instrument, is it's a fairly inexpensive test, and you can see in the well, and it's fairly cheap compared to running a wire line in the well. And the paper that we published in 2006 talks about how the wire line, when we run the wire line in a liquid loaded well, it actually changes a gradient. And we had a pressure bomb, and we could see that the gradient changed because the wire in the well provided an easier path for the gas to flow up the tubing. It punched through the liquid, and if gas flowed up the wire, and it actually increased the velocity of the gas and reduced the gradient. So it doesn't disturb the well. It's important when you shoot fluid levels. So this is a slide that we use quite a bit, and I like it because it's trying to explain what a fluid level shot kind of is. And so when you attach your gas gun to the well, and you're going to shoot a fluid level, then there's a difference in pressure between the gas gun and the well. And the valve in the gun quickly opens, and that difference in pressure is equalized suddenly, and that is the bang. The change in pressure is the bang, the shot's fired. And so that event of the valve quickly opening and the pressure equalizing either into the gun or out of the gun into the well creates a shot. And the shot, in effect, pushes on the gas at the surface, or pulls on the gas if it's an implosion shot. And the pressure wave that is created, it's like a big hill of pressure, travels through the gas at the speed of sound. Now, we call that acoustic velocity. So if we say acoustic velocity, we mean speed of sound, and it's the speed the pressure wave travels through the gas, and that speed is controlled by the composition of the gas gravity, is controlled by the pressure and the temperature. The bigger the pressure wave, the more differential pressure. It doesn't change the speed. It just makes more energy and lets you see echoes deeper in the well. So more pressure difference just means that the traveling wave that travels, the pressure wave that travels, has more energy, and you can see deeper in the well because of the increased pressure. But it doesn't change the speed the more pressure you put in the gas gun. Now, every time this pressure wave goes through a change in cross-sectional area, a portion of that wave of energy is reflected back to the surface, and that creates a thing we call an echo. And so the energy is decreasing as a pressure wave travels. Now the energy decreases less when the pressure is high. It decreases quicker when the pressure is low, so that the echoes are the reflection of a piece of the pressure of the traveling wave that's traveling down the well. And the bigger the reduction of the change in the diameter of the wellbore, the bigger the echo, or the bigger the echo is a kick, a pressure wave, a hill, and you'll see it on the acoustic trace. So we shoot fluid levels to see the echoes in the well from collars and liquid levels and changes in cross-sectional area, and these are the definitions that we typically use when we talk about shooting fluid levels. Now, this is a slide that is on two gas wells or plunger lift wells, and the title says, you can use a fluid level shot to alert you to what's wrong. And so on this well right here, here's the shot goes off, bang, the shot goes off, and here's the collars you can see. It's down the tubing, it doesn't get very deep in the tubing, count collars, but you can see some noise there. I don't know what that is. Maybe it's some corrosion, but we don't know. And then there's a down kick, which means a decrease in cross-sectional area. An obstruction, it's a tight spot, and this well had the example is called plunger stops in a tight spot. And when they dropped the plunger fell down the well, and it stopped right there because inside the tubing there wasn't supposed to be, but in this well, there was a decrease in cross-sectional area that caused the plunger to stop. And when we opened the well up, then the plunger would come up really fast and dry at the surface dry. And then here you can see the end of the tubing, which is an increase, and that's an upkick. Now this well had a little hole in the tubing, about 1/8 of an inch diameter, and the operator suspected there was some kind of problem because the plunger only came up about 20% of the time, and the hole, he didn't know there's a hole, but he suspected something's wrong. So we shut the well in overnight, and the pressure built up to about, I think, around 500 psi. And we shot down the tubing the next day. Then he sees a big upkick right there, a very sharp upkick. And now, often people say, can you see how big something is? Well, sometimes when something's tiny, then the upkick is narrow. When something is big, the upkick is wide. So in this case, it's a tiny hole, and it's not a very wide kick, but it's very sharp. So there's the upkick, the hole, and this kick wasn't supposed to be there. So at 5,000, a little after 5,000 feet, that's just supposed to be tubing with no damage. And so when you shoot this fluid level, you see, oh, there's damage, and there's a hole that's inside the tubing. There's a leak, an increase in cross-sectional area, and the bottom of the tubing had liquid still in it. So we didn't see the tubing wasn't dry. All the liquid wasn't pushed out. So you can see by shooting a fluid level, in many cases, what's causing your gas well to have problems just by shooting a fluid level. All right, so what can you see when you shoot a fluid level? Well, you can see is gas flowing based on the pressure buildup at the surface. And based on the area of the well, we can calculate the gas flow rate, area of the tubing and the casing. What is the depth? You can see the depth to the top of the liquid. That's a pretty typical thing from a fluid level shot. If you shoot down the casing, you see if liquid's above the formation. Typically on a gas well, when you shoot down the casing, if it's flowing through the tubing, the liquid level is going to stay right at the end of the tubing on the fluid level shot. And when you see a liquid level in the tubing, if you're below critical rate, you know that liquid is pushing on the formation, its weight, pressure, and it's causing the casing pressure to rise, and likely the well is liquid loaded. You can see, based on the gas flow rate, the percentage or the gradient of the liquid, especially that works really well if it's below critical rate. We use the Echometer S-curve to calculate the liquid in the fluid column. If there's liquid accumulation in the tubing, it's going to cause the casing pressure to be higher and to support that liquid in the tubing, and it's going to restrict the flow out of the formation. So we can see that. So we can see this idea of pressure. If the pressure's high, it's going to push all the liquid out. If there's no standing valve or the tubing is not horizontal, sometimes it's hard to push tubing out of a horizontal pipe because it's going to lay on the low side of the pipe. We'll talk about all that in a little bit. How much, and you can see how much it's restricted by the pressure of the liquid in the tubing. We'll talk about that in a little bit. We can calculate the pressure at the end of the tubing, at the reference at the bottom, both for producing and static. And you can see if the pressures push the liquid out of the tubing, and that's a common problem that you have when you shoot a fluid level. If you go to a well and shut the well in for 20 minutes, and the well's liquid loaded, you might shoot a fluid level down the tubing, and you might not see any liquid. And so one of the problems with this sentence here is that that's normal. The pressure builds up when you shut the well in because the gas is flowing through the tubing. And as the pressure builds up, if there's no standing valve with a ball in it, or if the tubing's not set near the bottom of the perforations, then typically the gas builds up and pushes the liquid out. So you need to shoot the fluid level right when you shut the well in and not wait around 20 minutes because it's going to change conditions in 20 minutes. We can show some examples on that. And then we calculate if you know the reservoir pressure and you know the producing well pressure from a fluid level shot, we can calculate the potential of the well. Now this is the idea this is the example of the well. Plunger hole in tubing is the name of the TAM example. And this shows the depths, and here's the shot going off. And the pressure was around 500 psi, so we counted collars all the way down to the hole. And so we can use the collar count method to get the hole, but there's not really a marker, so that's probably the best method we have. And if you can't count the colors by shooting down tubing, sometimes you just have to use the gas gravity and the pressure, average pressure and temperature in the well to get the acoustic velocity. But usually you can count colors if the well's quiet and it's not too much liquid shooting down the tubing. So this is an increase in the cross-sectional area. It's an upkick. And this is a decrease, which is the liquid level that's blocking the tubing. It's a downkick. So a decrease means downkick, an increase means upkick. And you can see the shot go off. The shot usually is a high amplitude signal, which means it goes really high. And the software, the TAM software, TDM software, picks the beginning of the shot based on the threshold voltage. So you tell TAM, look for a signal around 100 millivolts or 200 millivolts based on, and this right here is 31 millivolts, so it's even higher than that. And when TAM sees the signal on the acoustic trace at your threshold voltage, it makes that the beginning of the shot. All right, so this is getting into something we call flow regime, and we're going to talk a little bit about this what we call the transition. And the transition is where we use Turner to determine whether the well is liquid loaded. Here we're liquid loaded, and liquid is accumulating because the velocity of gas is too low, and the gradient, the change in pressure versus depth is high, which means there's more pressure back on the well per foot because liquid's accumulating in the tubing. On this side of this plot, we've got annular gas flow, which means the liquid's film is on the side of the tubing, which is normally above critical rate. And the film, if you're above critical rate, is going up, meaning it's unloaded. And if the film reverses, then little droplets of liquid start to fall off the well. And the droplets are typically fairly large, and they fall down, and the film goes down, and accumulates in the well and starts to load the well up. And this churn flow is probably more of a case of being liquid loaded and less. It's where the transition is starting to occur and more liquid's accumulating in the well. And it's usually it's based on the velocity of the gas. So typically the velocity of gas is what determines this what we call a flow regime. This is bubble flow, slug flow, churn flow, and then annular is when you're above critical. And it's like mostly gas. So this is what you would use if you went to a well and you didn't have a calculator. You just use this piece of paper, and this would be printed out. I've got a PDF file of this on your files that you download. And Jim Lee and I made this probably in 2005. And I typically use Turner because Turner's a little bit conservative, and it says if you measure the surface flowing pressure, which is you could go when you go to the well, and you know the gas flow rate. And we're going to assume you should be using the conditions at the surface. We just talked about that when we first started the presentation. And that's discussed more in the paper by Sutton that we included. So if you have a certain flow rate, it looks like about 310 MCF per day at about 110 PSI for 2 and 3 inch tubing, then if you're above this 320, 310 MCF per day, then the gas velocity is high enough to get the liquid out of the well, and you're not liquid loaded. You're above the critical rate. But if your gas rate is below 320 and the tubing pressure is higher or at 110, then you're going to be liquid loaded, and you would, if you shoot a fluid level down the tubing, you would see a liquid level. And so this is I use this chart not only to think about the well needing artificial lift, but it shows that I should see a liquid level. So if I go to the well and shoot a fluid level and I'm below this line for a certain size tubing for these conditions, I'm going to expect to see a fluid level in the well, in the tubing. And it's because it's liquid loaded and the liquid's being not carried out of the well, and it's causing the well to make less production. And you need to intervene into the well and add some type of artificial lift. Now, this is the spreadsheet. So on the spreadsheet, I've included this critical velocity calculator, but I also included a correction for hole angle, because if you get below the kickoff point, you're typically not vertical, and Turner was done with the vertical on vertical wells, and this is the calculations for a vertical well. And so all you do is you type in the pressure and you type in the temperature. This would be average temperature and average pressure. And this would be at the point. So if you want to calculate at the bottom of the well or the surface of the well, you type in this information, you type in the gas gravity, you probably leave the liquid density alone, which is salty water. This is surface tension typically for water. And this is, and there's a little drop down here, you can't see it. You put the tubing ID in, and then it calculates the Turner critical velocity in feet per second at this pressure, and the flow rate required in standard cubic feet and it gives you this velocity at that pressure and temperature. And then it's also in meters per day, which many people use versus cubic feet per second. And this is Coleman. There's a discussion of Coleman in that paper by Sutton. You can read about that if you're interested. Basically, Coleman is about like 20% less than Turner. And usually if you use Coleman to predict liquid loading, the well's liquid loaded when you're at Coleman's critical velocity. So I prefer to use Turner and be a little more proactive and think about this well's probably about ready to liquid load or it's loading right now. So that's the difference to me than Turner and Coleman. Coleman is just 20% less. So what do you see when you go shoot a fluid oil and gas well? Now, it depends a lot whether you're liquid loaded or not. If you're below critical rate and you shoot down the casing, you're going to see the end of the tubing and likely a liquid level. If you're below critical rate and you shoot down the tubing, you're going to see a liquid level in the tubing, unless you shut the well in too long before you shot the fluid level. And if you shut the well in too long, sometimes just 20 minutes or less, then all this liquid accumulation in the tubing is going to get pushed out. So you have to be kind of cautious about shutting the well in and waiting around to shoot the fluid level. Now, if you're above critical rate, again, you would probably see the end of the tubing if there's no packer. So if you shoot down the casing, you'll probably see end of tubing, and then the tubing will be filled with a mist all the way to the surface, and your first shot, you won't see anything except maybe a high fluid level. And then as you keep the well closed in, the gas and the mist will separate gradually, and the gas will collect, dry gas will collect on the top, and the mist will stay on the bottom, and it'll stay a mist as you gradually build pressure and push the mist level down. So that's what you'll see. And if your well has no liquid, which is very uncommon, and you're flowing above critical rate, you might just see the end of the formation, but you might see the bottom perf. But anyway, that's what you'll see. Now this is some data from Holland, from the Netherlands, and University 2 Delft did this, and they're looking at velocity of fluid through gas, and they're videotaping this at high speed. This is a small pipe, and you can see across the bottom the velocities. And over here, if you look, you're liquid loading, and if over here you can see the film on the tubing is going up, and the gas is in the central core of the tubing and is carrying all the liquid out. And then over here, a slightly lower velocity is still going up, but you're starting to see a few droplets, those little round circles. Let me start it again. A few droplets starting to fall off the tubing wall, but they get reabsorbed in the wall, and are still the velocity both of the film and the gas are going up. So it's above critical rate. Now here, this is probably the transition around 10 meters per second. We're starting to see droplets, these big round circles going down, and it's kind of swirling a little bit, and it looks kind of mixing, and we're starting liquid load here. But now we're liquid loaded in this case, and you can see big droplets, and the droplets are typically falling down, and those droplets are usually what Turner based his critical rate on. And people have said, oh, that's not a very good method. You should use the film velocity. If the film's going up, it's above critical rate. If the film's going down, it's below critical rate. It's a lot more complicated to calculate. The droplet method Turner developed you see the droplets, even if you think about it, you see the droplets here, and it's a fairly simple method. So I really am an advocate in using Turner for a critical rate. This is just trying to show the same data, and what it's trying to show is that here's the same plot. The blue line is for 2 3/8" tubing, and if you're below the line, you're going to have a liquid level in your tubing. That means you're below critical rate. If you're above this line, you're going to have mist in the tubing. You'll be flowing all the liquid out of the well, and that's really what this represents. But this is typically used at the surface where the spreadsheet would be used at any point in the well. All right, so here are some wells in different locations in the world. This is a gas well, and in fact, the picture of the well that's behind me, I think this is this well right here. And we were to shoot fluid levels on wells in Holland because they couldn't see the liquid level with the equipment they were using. Well, the problem is that in Holland there is a lot of people, and in Holland they decided that they needed to protect from any kind of release, and so in all the onshore wells in Holland, they have installed a subsurface. They at the time I was there, they all had it installed in every well onshore, a subsurface safety valve that reduced the height of the tubing by 2/3 from about a depth of 2,000 feet. So liquid would tend to accumulate on that subsurface safety valve, and often they couldn't shoot past it. So I took this large volume chamber with a remote fire gas gun, and it makes a lot of energy in the shot. This wellhead pressure is like 300 psi, and we could see all the way out the end of the tubing where they couldn't see that at all, and we could see the liquid level down in the perforations. So this gas gun worked without a problem, and sometimes you have to pick the right gas gun for the right well conditions. This is the compact gas gun on a plunger lift well. We're shooting through the tubing, and we use a compact gas gun because we can do a plosive shot. Low pressure has a somewhat larger volume chamber, so we typically like this gun because if we track a plunger, we can cock it and keep the liquid from coming into the gun body when it unloads liquid to the surface. Whereas a remote fire gas gun, you have to charge it to high pressure. You must use nitrogen gas to charge it if you use it to track a plunger, because the CO2 gas will absorb into one or more of the O-rings and cause them to get the bends and pop when you release the pressure. So you always should use nitrogen gas when you're tracking a plunge lift well. But the compact gas gun usually works well. Now this is a high pressure well, and so we were using a high pressure gas gun. It's right up to 5,000 psi to shoot fluid levels. And this is a well. This is over in East Texas. This is a well up in west central Wyoming, and we're shooting down the tubing on a well flown above critical rate. So there's different kinds of liquid level surveys you can do on gas wells, and you can have the liquid level that will move with change in pressure. That's one type of test you might do. Maybe the liquid level doesn't move, and that would typically be a well that might be shut in, or maybe there's a standing valve in the tubing that traps the liquid. Or you could pump something into the tubing, and you may want to track it as it falls. And what we found, but we won't talk about this in this presentation, but what we found, if you dump some liquid surfactant into the tubing, it falls very, very slow. Initially, maybe 3 foot per minute, and then in the first 45 minutes, it may only it'll fall less than 50 feet per minute. So it's really slow how fast surfactant falls down the tubing. We've done several tests on wells like that. And then liquid levels in tubing and casing. And so these different things are just some ideas about you can shoot these kind of fluid levels, and we'll talk about them a little bit more. So if you're going to shoot a static fluid level, what the idea is that the well is shut in and it's stabilized and it's quiet, and you can shoot multiple shots down the tubing, and you should take at least 2 shots, and a liquid level kick should repeat, and you shouldn't see an increase in pressure at the well if it's actually staticked out. You know, a lot of gas wells have really high static pressure, and it may take quite a while, and so you may have just some limit on the amount of pressure buildup that you allow to declare the well as static. So, but you take a couple shots and make sure there's no pressure increase and the fluid level is not changing. And then on a static well on the casing, you'll take a couple of shots down the casing. It's easy to shoot, and if there's no packer, you'd shoot the casing to shoot a static fluid level. In fact, you may shoot the casing first if you shoot a static fluid level, and then shoot the tubing if you want to shoot both. But if you have a packer, you can't see past the packer because that's just a pressure seal. But if there's no packer, you just take a couple shots and make sure they repeat, and you can go on to the next well. Now, this is a picture about an idea about when does a gas well load up. In a gas well, the gas carries liquid in the tubing, and it loads when it's flowing. And when you shut the well in, the gas flows in, continues to flow in the well, and the velocity is dropping, and the pressure is increasing, and it's starting to depress this liquid level right out of the tubing. And once it's shut in for enough time, maybe more than, in most cases I've seen 20-25 minutes, if there's not a lot of liquid, it'll push liquid out of the tubing. And you shoot the well, you'll see the perforation, you'll see in the tubing, and that's pretty common on a gas well. And you can see that the liquid gets pushed out when it's shut in, and the liquid gets carried in the tubing and requires increased casing pressure to hold that liquid in the tubing. And the increased casing pressure pushes on the formation and restricts the inflow. Now here's a well that they went to, and this is that well up in Wyoming, and it had been shut in for 6 weeks, and it was stabilized. And you can see that I'm saying here that the velocity of the gas is 0 because the pressure didn't build up at the surface. So this well was static to what we call static out, or at static pressure. And when we shot the fluid level, we could see very clearly all the recesses in the tubing, all the way down to the top perf. In the top perf right there, and then liquid levels was just above the bottom perf. So this well, there was no gas flowing in and no liquid flowing in the wellbore, and the pressure had stopped it. The increasing gas pressure had stopped it and equalized at the bottom of the well, and the pressure stopped changing the surface. It had been shut in for 6 weeks. It doesn't always take that long, and that tends to push all the liquid back out in the formation and the fractures, the perforations, and this is what you'd expect. In fact, since probably 1981, I've known that, because I got lectured on it, that if you shut a gas well in, the liquid level is always at the bottom, and it's not always, but it's often at the bottom, and that's why you shoot it. You want to find wells that the liquid level is not at the bottom on a gas well, because that means there's liquid accumulation. You have to be cautious about sticking your tubing below the static liquid level, because it's not going to want to unload very well. So here's the report in TAM of this well, and you can see that we have a gas column from here to here, and that's the pressure at the surface was 2,249 psi, and the gas column added about 360 psi of pressure, and then the gas-free water didn't add, probably less than 40 psi, and the pressure at the bottom of the well is well, I don't see it on this report offhand, but there's our static. Oh, there's right there, 2,642 psi at the reference of the bottom, and that's the bottom perforation is the reference. And you can see here the pressure didn't build up. And this is a well we can look at later. We shot quite a few fluid levels on this well as we depressed the mist out of the tubing. So we'll look at this later. So the idea of transient means that you're going to increase the pressure, and the pressure is going to move the liquid level, and the liquid level moves based on the gradient of as long as it's stabilized and the gradient doesn't increase, the liquid level moves based on the gradient of the fluid. And in a gassy column that's really light, it can go below the end of the tubing, and this is important. It says requires good communication with operations for planning. Why would it say that? Because if you just go out there and say shoot that fluid on that gas well, and the operator that shoots the fluid goes out there and shuts the well in sets the tubing in to get ready to hook his gun up, and he drains some fresh liquid off the valve, and he does some other things, and he hooks his gun up. By that time, the conditions of the well have changed, and it's not going to be representative of the normal conditions of the well. So when you talk to somebody about going to shoot a fluid well, you say before you shut the tubing in, you hook your gas gun up, and as soon as you close that, open that, shut that well in, you open that valve, and you shoot that liquid level down the tubing on that gas well, because we want to see the conditions in the tubing when it's normally flowing. And so the pressure in the gun, if the fluid level's down deep, you're going to need a high pressure to see deep. If it's fluid levels at the surface, you're going to use less pressure to shoot the fluid level. But this is talking about you need a big shot to see deep down the tubing on a well that's flowing. You may need to look at the data in more detail to see if you can, you look at your casing shot, look at your tubing shot, make sure the flowing well pressure is reasonable. Why? Well, the pressure at the end of the tubing ought to be really close from the casing shot and the tubing shot. And so that's a good check. That's a good check that you can use. So if you have when I first talked to a guy out in the field about a gas well flowing above critical rate, he walked over to the wellhead and he opened the valve and let some gas flow out of the tubing into the air. I said, what's a well look like above critical? And right there in front of me there was a little cloud, and he said that's what critical rate means. When you think about a well flowing above critical rate, you're supposed to think that all the liquid is being carried out of the well as a fine mist, a uniform mist. The velocity of the gas is high, and if you could make it come out of the well just like this, you'd see a cloud. And so that's above critical, and that's what I saw, and that's why I put that little picture right there to try to make me remember that the gas rate in the tubing, and the casing's bigger, so there might be liquid down here. Lower velocity might accumulate liquid first in the casing below the end of the tubing, but the gas is flowing as a mist from the bottom of the tubing all the way to the surface if you're above critical rate. And it's fairly uniform because the velocity is not changing much and the liquid composition is not changing much versus depth. And so here's these fluid level shots. So we started shooting this well, and the first shot was at the surface, and this is in the second shot, and we can see an echo. Now this well has a cloud in the tubing, and a cloud in the tubing is a mist. And so if you think about this kick right here, and that kick, and that kick, and that kick, and that echo, those are the echoes in the tubing. Five minutes, excuse me, 5 minutes apart, and these echoes are the echoes off the top of the cloud. And what does that mean? That means that how much pressure difference does it take in the fluid to make an echo? It doesn't take much. And these are spaced about 5 minutes apart. And this is the plot of the data. So these points right here are the pressure at the top of the mist. And these points right here are the pressures at the top of the surface, And so this is the first shot, the liquid is at the surface. And as the pressure builds up, the pressure is increasing, and the mist level is pushing down, and it's almost a straight line, and a change in pressure versus depth, you can calculate it, and that gives you the gradient of the gassy column, and the gradient, this line, is about 0.018 psi per foot of this line right here, and the gradient of the fluid right here, the mist, is 0.028, 0.026. That's about 50% heavier, and we can extrapolate this down all the way to the bottom, and the bottom flowing pressure is 804 psi. And this is a well early on that we looked at that was flowing very close to or a little bit above critical rate, and we could see the mist in the tubing, we see the light gradient, and we depress it from the surface down to the bottom of the well. Now, once a well starts to liquid load, then it's common to want to keep the well flowing like a gas well above critical rate. So, and often the first method used to maintain flow is to add surfactant to the well. And so this is a well in the Barnett Shale where they're injecting some surfactant down the casing and it's flowing up the tubing. And this is a fluid shot down the casing. Here's a shot going off at the surface. This is the name of the well. It's an example. This is an example file. You can see right here there's an upkick at the top perf. There's a top perf. And there's a little upkick at the end of the tubing. The fluid level is right below the end of the tubing where it should be because the casing valve is closed and all the flow is going up the tubing. The pressure here at the surface was, let's see here, 150 psi. And then from 150 down to the bottom is not much more pressure, about another 30 psi, 29 psi. So this is the way the gas column is, about 29 psi. And so we know this pressure gradient very well because we can calculate it based on the acoustic velocity and the pressure and temperature in the well. So we know this very well. It's a very accurate calculation. And so we're very confident that this pressure right here in the tubing is very close to 180 psi. Because we measure surface pressure and we very accurately measured the acoustic velocity of the gas based on counting collars, or you can use this marker right here and get a very accurate gas gravity and accurate pressure. And so we're pretty sure that's the pressure right there. Now we shot down the tubing and we see this high liquid level in the tubing, and we can calculate the way this fluid based on loaded liquid. And so in the software, TAM and TWM, we assume that this liquid is liquid loaded. Well, there's not a button in TAM yet to click and say this is a mist, which causes surfactant. And so since this is considered loaded liquid, it's 24% liquid, and that's going to be TWM and both in TAM. And that's a gradient that TAM would use. And then we calculate this bottomhole pressure as 560 psi, which is in fact incorrect. And so when you're shooting a well that's treated with surfactant, you probably ought to shoot it before you drop the soap stick because it's going to lighten the column and make the gradient less. It's going to change conditions, or you need to think about it being probably less if there's surfactant in the well. So that's just a caution because the surfactant you use to lighten the column is going to change the gradient, and the software, TWM and TAM, are going to think that it's liquid loaded, not a mist, which would be, a mist would be at least one third lighter. And so when you look at this chart, this is a gradient that you'd expect to see when you have surfactants, which is lighter than this gradient right here that's liquid loaded. And so this is a well, this is a 10,000 foot deep well, and we're looking at the surface pressure of 300 psi. And if you have no surfactant, the gradient's going to be around a 0.08, 0.09 psi per foot, and it's going to add more pressure, this much more pressure than if it was flowing above critical rate. So if you can make the well flow above critical rate, then you're going to have much lower pressure and much higher production rate. And that's why you don't want it to be liquid loaded, because there's this extra pressure acting on the formation. And so if you use Turner and you say, well, you're below the velocity required to get the liquid out, you're liquid loaded, then you're going to be a liquid gradient somewhere in this range or higher. If it's all water, it could even be higher than that. So it can be really heavy. If it's gas flow, this is 0 barrels of liquid, and this is 50 barrels of liquid. So the mist flow is 0 to 50 barrels right there, and it slightly increases the gradient based on the amount of liquid present. And if you add surfactant, you can move this line from here, liquid loaded, over to the mist gradient line. So if you're liquid loaded gas well, you have the light gas on top, you have liquid below, and we assume in TWM and TAM that the liquid is divided based on the oil and volume rate produced from the well. So this is like 1.2 barrels of condensate and 0.8 barrels of water, and that's what these heights came from. And we shot down the tubing on this well, and it's a high fluid level, and we'll talk about that in a little bit on an example. The well stabilized. It's got a lot of back pressure on the formation. This weighs quite a bit, pushing on the formation. We use the S-curve to calculate the gradient that we developed at Echometer in 1986 and 7, and it's a good method to calculate the gradient of wells that are below critical rate. And so here we shot the fluid level, and here's our high fluid level, and it's 8,636 feet of gassy height. The pressure built up right here in about, this is pressure in time, this is time here in 2.5 minutes. This is 2.5 minutes here. And the pressure built up about 16 psi in 2.5 minutes. And that means at the time we shot this fluid level that there's about 135 MCF of gas flowing up the tubing, and it's about 19% liquid. Well, what does that mean? What's 19% liquid mean? It doesn't mean that there's 19% of the column is liquid down here. It means that the gas is flowing through this entire column, and the liquid is distributed, held up by the gas flow from the bottom of the well to the surface. And if you could, which you don't have, a magic wand, there's no such thing as that, and you could take all the gas bubbles out, then this tall gassy column would be the equivalent of this 1,615 feet height to calculate pressure. So this is the equivalent height of this column in terms of pressure to calculate pressure at the bottom of the well. And that's what this Echometer S-curve does. And so if you look at the Echometer S-curve that's in a 1986 paper that's on our webpage, you can see that it looks like an S, and that's kind of an S. And we go to the table, and we have 15.9 psi build up in 2 minutes, so that's the change in pressure over time, times this equivalent gas-free height. That gives us the point right here. You come down this chart, and that gives you the percent liquid of 19%. And that's where this equivalent gas-free height comes from to calculate the pressure at the bottom of the gassy column. We use that to calculate the pressure. Now, when we look at the TAM software, there's a report for flowing gas wells. If you shoot down the tubing, is the liquefaction tab. And what it shows the gas gradient if there's no liquid. That's the flowing well pressure right there. And this is the actual gradient of the liquid in the well. So if you look right here, this liquid right here, we're saying is this gradient, change in pressure versus depth. At the bottom of the tubing, there's this much back pressure. So here's the back pressure acting on the bottom of the tubing, which causes the casing pressure to be high. So our casing pressure is higher, required to hold this liquid in the tubing, this 630 psi pressure, and the well is liquid loaded. So based on the tubing sizes, if your tubing size is 1.5 inches or less, you're going to stay liquid loaded. If you're 1.25 inches or smaller, I said it wrong, 1.5 inches or greater, it's going to be too large of area and too low velocity, you'll be liquid loaded. And if you're smaller than 1.25 inches, then you'll be above critical rate because the size of the tubing is small enough to increase the flow rate of the gas that should be above the critical velocity for water, which is an MCF per day of about 1 million per day in 2 7/8 tubing, or less gas of 360 MCF per day, 1.25 inch ID tubing. And so this is our deliquification tab, and it's showing the wells liquid loaded. Here's our back pressure. Now, when you shoot down the tubing, you'll see the gassy column, and if we shot down the casing on this well, and we see this echo right here, and if you look at the echo right there, there's an upkick, and the liquid level is right at the end of the tubing. So while the well is flowing up the tubing, we shot down the casing, and we measured the fluid level depressed as the pressure built up, but the casing shot showed an upkick right at the end of the tubing. And so this well is a fairly deep well. It's over 10,000 foot deep. The end of the tubing is 11,261 feet, and it could be a marker because there's our upkick right there. And our liquid levels is right there below the end of the tubing, and that's normal. And the acoustic velocity in this well is 1,315 feet per second, and that's a methane gas gravity of about 0.66. And so this is what you should expect to see. We've zoomed in to this area in red. This is what we did. We took our mouse and drug a little dot over to that point right there, and pull this point up to right there, and just look at this one little window. And this is the window we're looking at from about 10,000 feet down to about 11,000 feet in the well. Now we can see this blown up echo here showing the upkick on the acoustic trace. You can calculate the height of the liquid based on the pressures, and you can calculate the volume, and you should see a liquid level in the casing at the end of in the tubing if there's no packer. And on a liquid loaded well, and you're below critical rate, you should see a liquid level in the tubing, and you can use that equation to calculate it. But it's not going to work. These equations don't work if you're above critical rate, or you have surfactant. If the well's not been shut in for very long, it's you can shoot down the tubing and get a reasonably reasonable pressure. Remember, same valve can hold liquid in the tubing if it's present. So here's our comparison. We shot down the tubing, and the pressure from this tall gassy fluid level right here at the end of the tubing is 1,078 psi. There's a pressure to the liquid interface, and here's the pressure shooting down the casing. And they're they're not exactly the same. They're about 60 psi difference. But this is only 8,000 foot liquid, and being off maybe 60 psi isn't that bad. So this is a comparison between the tubing pressure is 358, casing pressure to surface 775, and we can see that the pressure at the bottom doesn't quite match, and we probably slightly overcalculated the gradient right here. All right, what happens when the tubing's set high? Well, if you have a well that's liquid loaded and the tubing's set high, and you start to build pressure, then, well, how could you do that? We put a gas gun on the casing, shot down the casing. We put a gas gun on the tubing and shot down the tubing, and we determined the distance to the liquid on the tubing and casing shots. And so here is the plot of the liquid level in the tubing going down. As the pressure built up, we shut the well in. These are increasing pressure. We increased from about 140 psi up to about 410 psi during this test as we gradually built the pressure up and pushed liquid out of the tubing. But it's important to understand that in the paper we talk about the liquid level collapsing. And if I show you that slide, let me show you that paper real quick here. Right, so here's the technical paper that was published in 2006, and it shows this liquid level here. This is the liquid level here. That the liquid level collapsed, and the gradient, these lines are gradients, and the gradient gradually increased as we kept the well shut in. And in this case, the tubing was at the bottom of the perforations, and the liquid level didn't leave the tubing and was held in. Whereas in the presentation that we have here, all right, so this is showing that the liquid level gradient didn't change. And so one well, I just showed you in the paper that the gradient of the gassy fluid column changed, that was liquid loaded, and this well didn't change. And the difference is that this tubing set above all the perfs. And so the depression is a straight line. And if the tubing set deep, then the liquid's held in the tubing and the gas flow stops, and the gradient increases as the holdup goes away. All right, so here's the tubing pressure at the surface in this ugly color, and here's the casing pressure, and you can see that during this time when the well shut in, the difference between tubing and casing pressure is getting less and less and less. That means that the liquid's getting pushed out of the well. At this point, all the liquid gets pushed out of the tubing, and at this point, that the tubing and casing pressure are equal, all the liquid's been pushed out. Now, so this is the shots that we took on the well, and there's different pressures, and this is the gas flow rate into the casing, gas flow rate, and this is the gas flow rate into the tubing. And you see that there's a lot more gas flow in the tubing than into the casing. Well, that seems kind of weird, because down at the end of the tubing, there's just tubing and casing annulus. And how does the gas know to go in the tubing and not go in the casing based on the area? Well, it does. It doesn't go into the casing. It just a little bit goes in the casing, but most of it goes in the tubing, which seems kind of strange. And so the 2.5 barrels in the tubing got pushed out in about 55 minutes out of the tubing. And this is a detailed plot that shows that here is the casing pressure buildup, and here's the tube pressure buildup, and right there is when the liquid got pushed out of the tubing. And at this point right here, there's 21 MCF of gas flowing into the casing, which is 19% annulus, which is 19% of the flow. And here, there's and 78% of the gas is flowing into the casing over here, and only 21% of the gas is going into the tubing. And so this is kind of weird. This gas is smart. When there's liquid in the tubing, the gas knows to flow in the tubing. When there's no liquid in the tubing, the gas flows up the casing based on the area. And so that's what this shows. This shows is that when the tubing is set high, preferentially the gas goes where the liquid loading is and pushes the liquid out to maintain the pressure at the end of the tubing. And once all the gas has pushed liquid out, then the gas flows into the tubing casing based on the area, when both the tubing and casing are annulus areas. Tubing area and casing area is open to the gas flow. If there's no liquid in either pipe, then it flows in equally based on the area. But if it has liquid in one or the other, then the gas goes into the heavy gradient and pushes the liquid out. If you're above the formation. If you're above the bottom of the formation, it does that. Now this is that critical velocity equation we saw back in the spreadsheet, and this is the term that's used to correct for critical flow. And I said it wrong. This is a term that's used to correct for hole angle. And this is the way the plot looks. This is a plot. So this is 0 is vertical, and 90 is the angle of the flat horizontal well. And you can see here if the well's about 40 degrees, at 37 degrees, you get an increase in the critical rate by about 35%. So the angle of the tubing has a big impact on liquid loading, and it requires more gas to get the liquid out of a well if you're not vertical. So here's a well that we shot fluid levels on, and it's vertical down to the kickoff point, and then it has a deviation below the kickoff point, and there's our end of tubing. And so this was a well where we shot 6 fluid level shots, and we were able to measure the gradient, and the gradient was a lot heavier than it would be if it's a vertical well, liquid loaded. And we see here that we have a 1.78 gradient, the slope of this line, and we pushed this liquid out in less than 20 minutes. And so when the operator was shooting fluid levels on this well, he would shut the well in for about 20 minutes before he shot the fluid level, and then he would see no liquid in the tubing, and the conclusion was the wells weren't liquid loaded, but they were, because the procedure was causing the problem. So it's important not to shut the well in and push liquid out. It's also important to realize that the liquid can accumulate more liquid in the well when the tubing's not vertical, because the liquid load pressure rests on the side of the tubing. And that's what this says. You know, it took 17 minutes to push liquid out. There's 2 times more liquid than it would have been if it was a vertical well, based on the gradient of being twice the 0.08 psi per foot in a vertical well. Stratified flow. So we're getting kind of short on time, so I'm going to just kind of skip through this description here and just talk about during the slides. And we presented this before quite a bit. Now this is a well that we shot with TWM, and it's in the example wells. It's called horizontal mandrels. And when we shot the fluid level in TWM, we only had an option for standing C nipple or the end of the tubing, and so I use the CD nipple as the end of the tubing. And so when I look at this data here, it's confusing to me because there's some upkicks that don't seem like they belong. And so once we go into the TAM, we have a lot more flexibility on C nipple, standing valve, end of tubing, perforations. And so I re-entered the well bore schematic into TAM. Now in TAM, this is the well bore schematic, and now you can see that this upkick didn't match anything before, and now it matches the top perf. And this upkick matches the end of the tubing, and this upkick matches that perf, and this upkick matches that perf, and this is the horizontal section of the well. And so this is way out in the horizontal, and we're seeing liquid level way out in the horizontal, which is common when there's not a lot of gas. So this well is only making about, not very much, maybe 5 or 6 barrels of liquid a day. And so the liquid lays on the bottom, stratified on the bottom of the pipe, and the gas is on top. And you can shoot out the top of the horizontal pipe until you see a dip, and then you see the pipe is blocked, and you see a down kick. So this is a typical example of shooting level in a gas well, in a horizontal well, where it looks like the tubing just went past the top perf down in where it's horizontal, and you can see way out to a trap, a horizontal trap, where the liquid accumulate, and there's our down kick right there. So this is a deviation survey, and the tubing's out in the horizontal, and this is an overlay we need to fix of all the different liquid level, formation depth, and the tubing that overlap. But our liquid level is, let's see, right out there, out here in the horizontal. And this is an animation that Carrie Ann did. I really like it. And so when we shoot the fluid level, you can see the shot go off. And every time we go by a gas lift mantle, this is a gas lift well that has been converted to plunger lifts. The gas lift valves are still there. And you can see each of these gas lift valves show up, and you can see the kicks on the acoustic trace. And then you can see the up kick at the end of the top perforation. And then you can see the purse and liquid level. And this is a well where out near the toe, there's a slight drop in the well bore where the horizontal has a trap. It goes down and comes back up, and liquid collected in a low place, and that's what it made that down kick. And it's not uncommon to shoot a horizontal gas well and see all the way to the toe of the well, because a lot of these gas wells are toe up, and the liquid level is just going to drain down, and you'll see all the way if the liquid level production rate's not high. Now this is a slide showing a high fluid level, and the software in TAM doesn't pick automatically always the liquid level that's closer than a second to the surface. So what you see is on a high fluid level on a gas well, it doesn't pick it, and we don't see any collars very well, and the fields are asterisked in, and the program by default picks 8.5 seconds. So if you see a liquid level 8.5 seconds, you should think that the program automatically defaulted to 8.5 seconds, and the fields are blank because it didn't pick a liquid level, and it says automatic liquid level detection failed. You need to manually relocate the liquid level marker. So when we move the liquid level marker, well, if you go in and zoom and look at the liquid level, there's no down kick right here. That's 8.5 seconds. I don't see a down kick. That's not liquid level. That's just a resonating signal, and we count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's these echoes are 1/10 of a second apart, so likely liquid level is 1/10 of a second from the surface, because you can see these repeating echoes and how far they're apart. And so if you zoom in to the surface and look at the first second, you can see right there is the knee of the kick, and liquid level is 1/10, pretty close, 0.104 seconds from the surface. And that requires that you manually move that up here and zoom into it and pull this dot up and expand this scale. And we'll do that when we look at this example in a few minutes. Now, a packer. If you have a gas storage well, it's often the casing annulus is blocked with a packer, and usually the liquid, the casing is filled with kill fluid, KCl treated water. And so Ken and I went to this well, and we shot down the casing because the operator wanted to know why the pressure was high on his casing annulus. He thought he had a leak, and we expected to see a liquid level down somewhere deep. And when we turned on the low pass filter, we could see a down, and then an up, and then a down. And I said, I don't know why it kick's going up, but there's our liquid level. And we told the operator to order a certain amount of KCl treated water to fill it back up. And he called me and said, no water will go in the casing. And I said, well, that can't be right. We never make a mistake, which was not true. And we do make mistakes, just like everybody else. And after we went back and re-examined this data, we saw that there was a liquid level 0.02 seconds from the surface, about 15 feet. And so whenever you see a split level shot that looks like a funnel, and it's kind of like a high frequency noise, usually that's due to something high in the well. And so when we go back and look at this, see how it looks kind of like a funnel or a tornado and all this high frequencies? That's a signal to you that there's a high fluid level in the well. And you should look up here because, first of all, liquid level isn't there. It's somewhere up here, and there's no down kick right there. Well, this well, when we turned on the low pass filter, we'd see a down kick, and so that's probably liquid level. But what happens is when liquid level is within about a joint of the surface, less than 30 feet from the surface, then you can shoot a flow level with high pressure, and you can send a pressure wave through this liquid and echo off the packer. So this is an echo off the packer, and the acoustic velocity is 4,300 feet per second. And if we had thought about it more, maybe, I don't think we would have figured it out, maybe, I don't know. But after going back into another well and shooting it, we realized that you can shoot through liquid if the liquid's close to the surface, and that's what the shot looks like. And so this is down, and then this upkick is because it's like your gun is attached to a hole at the surface, and every time the wave comes back to the surface, it inverts the signal. So first it's a down kick, and then the next echo is an upkick because it's an inverted signal, because it came back out of this into the near the surface. So this is shooting through liquid. Now this next section is going to talk about holes in tubing on gas wells. And here's a well that's producing, and it has a fairly high rate, and this is over time. And then right about here it started having some trouble, and it fell off the decline curve right there. The Turner critical rate was about 320, and it fell off the decline curve at 820 MCF per day. So the engineer said to the operator to go out and shoot a level because they probably need to open the well up the sliding sleeve and get more gas flow, because the well is likely liquid loaded. And if he had looked at the spreadsheet or the critical velocity chart, he would have known that the critical velocity would meant that it should have happened way over here. And it should have been continued flowing for like another year. So the operator went out and shot some fluid levels and found a hole in the tubing. And there's a procedure here that you have to follow. The first thing you do is shoot down the tubing casing annulus. Why? Because the fluid level is supposed to be at the end of the tubing on the casing shot. And if you shoot down the casing and see a high fluid level, then that indicates gas is flowing up the tubing, and it shouldn't be flowing up the. I said it wrong. Gas is flowing up the casing, and you need to investigate for possible holes. So you need to shut the well in, build the pressure up, push liquid level down, and you'll start to see an upkick on the shots. So there's the hole. It's only an 1/8 of an inch diameter hole. It's a little tiny hole, 4,325 feet from the surface, and this is due to condensation at a certain depth due to temperature change. And that's where the fresh water rained on the tubing and eventually washed away or became acidic and took away the steel off the tubing wall. So here's the first shot, and the important thing to notice is that there's no upkick right here, even though there's a hole right there. Why is there no upkick? Because the tubing has gassy fluid above the end of in the tubing above the hole, and you can't see it. So you wait about 15 minutes, you shoot it again, and there's an upkick right there, and there's our liquid level. And notice liquid level is starting to move down. See liquid level move down, and you take another shot and confirm it, and shooting down the casing, there's an upkick. So we've got an upkick that went there before. Then we take our gas gun off the casing, put it on the tubing, and shoot it, and we see an upkick on the tubing shot, and at the same depth, not the same time, because the acoustic velocity could be different in the casing and the tubing. And then there's our next shot down the tubing and shot down the casing, and they show that there's an upkick that doesn't belong there, and there's likely a hole in the tubing. We'll look at that. That's the example right there. So what do we know about that? Well, the operator that found these holes found that 10% of 150 wells that they didn't expect to have holes in tubing had holes. And so don't be surprised if you have 10% of your wells have holes in tubing, you don't even know it. You should see a drop in production when the hole appears. You may think it's liquid loaded. The tubing casing pressure aren't equal because there's a gassy fluid column above the hole in the tubing, which makes the casing pressure not equal. So the conception that the tubing pressure and casing pressure equal isn't true if there's a hole. Only if the fluid level is pushed below the hole is it true. So it's a pretty simple method to find the holes in tubing with an acoustic instrument. This is one last slide here. Here we shot the fluid level on an offshore gas well, and you can see the subsurface safety valve, and you can see this obstruction down hole, like a landing nipple. And you see our liquid level. Well, I think that might be the anchor there, and there's a liquid level. And this is closed, and you can just see just the repeat echoes of this subsurface safety valve closed. So here it's closed, here it's open, you can see past it. And that's an example we'll look at in a little bit. So this is a list of things you can use fluid level float for on gas wells. You can determine liquid level and bottomhole pressures in liquid loaded wells. You can determine the gradient by depressing the fluid level. You can determine static bottom pressure by shooting the fluid level. A very accurate test on static fluid level because the well is stabilized and the tubing and casing are typically filled with gas, and it's very easy to shoot a level, determine accurate pressures in gas. Don't set your tubing below the static fluid level if you want the well to flow. You determine liquid levels in the annulus. You can test the integrity of tubing by looking for holes, looking for things like that. You can monitor a treatment, how fast it falls down a well. If you want to keep the well closed before it's down on the formation, you can monitor the treatment with a fluid level shot. We tracked plungers for a while at the beginning before we realized a plunger makes noise and you can hear it, but you can shoot levels and track a plunger or a batch treatment. The main thing you can gain is a knowledge about how wells work, gas wells work by shooting levels. And that's been a benefit, a big benefit of understanding how gas wells work is by looking at data we collect on gas wells. And also you can check to see if stand valves open or close. So with that, that's the end of the presentation. I hope you enjoyed the presentation. I went a little more than an hour. I kind of went over to my time. So Gustavo, are there any questions?
Yes, we have a few questions only. I'm going to start with the last question that I received from the private chat. It's related to slide 54, where we have the hole in tubing.
Right.
And it says, why the same tubing hole looks much bigger on the tubing shot than in the casing shot?
Well, if you look here, this scale here is 100 millivolts, and so the echoes from, and this is 31.6 millivolts, so it's even, if I made this 100, it'd make it look smaller. So the collars make a lot of noise and take up a lot of the energy from the shot, and the recesses don't seem to absorb as much of the trailing valve energy, and so the hole is the first big change that the shot saw. And so it makes a big kick there. Whereas here, the collars are making a lot of racket or a lot of reflecting the energy from the shot, and that reduces the amplitude of the echo at the casing. So the energy is less when it gets to the hole on the casing shot.
Okay, that's okay. We have more questions. Lynn, Ken is asking at the beginning of the presentation, slide number 4. When he's asking, can you always see below a tight spot?
Well, this was kind of a unique tight spot. It was a collar stop. This is a collar stop that was supposed to be held in place at a deeper depth in the tubing. And so the idea, it's got little latches that latch into the tubing collar recesses. And for some reason, it unlatched and it blew up the bumper spring, blew up the hole, and it doesn't have a standing valve in it. If it did, you wouldn't be able to see past it. But this is a bumper spring with collar stops held in a joint of the tubing that you can shoot past. And so the answer is, if there's a partial obstruction, you can shoot past it. But if there's an obstruction that the tubing is completely filled off, you can't see anything past that obstruction. It's just going to repeat echo. So you wouldn't see this if you couldn't see past it. That's a dumb answer, but that's the truth. If you can't see past it, you won't see any echoes that are different than repeats. So This repeat echo is going to occur at about the same 8-second frequency over and over again. So if you can't see past it, but you can see past it in this case.
Okay, I'm going to take just a very last question related to holes. There is a question saying, does a hole kick affect the color count marker?
I've got an example where it's even a split joint, and you can count colors all the way down to the liquid level pretty much. And generally, no. But sometimes the hole could cause an impact, and you can't see past the hole. So see, look, this is a casing shot, and even though I can see some colors here, it's not wanting to count past the hole because the hole impacts the way we count the colors. We try to count continuously down the wellbore, and we don't skip. If you were using 11-point dividers, you'd skip that and keep on counting colors. But the software says, ooh, I can't count colors right here, so I quit. So you probably can't count past a large echo because of the method we use to count colors. So in general, I'd say most of the time you'll have a problem going past a big echo, but sometimes you won't. All right.
One more question from Manuel says, what is the approximate percentage of liquid fallback in an annular flow profile in a gas condensate well?
Okay, well, there's a rule of thumb. And if you are liquid loaded and you try to vent the well, okay, then the rule of thumb is 7% of the liquid falls back per 1,000 foot of depth. So let's say you have a well that's 10,000 foot deep. It's going to lose 70% of the liquid load if you try to blow it out by venting the well. And normally you won't have any liquid come up because it's going to, even though it says 7%, that's most of the liquid won't come up. So the answer to that question is on a well that's liquid loaded, if you try to vent the well to bring liquid out of the well to unload the well, then you're going to lose 7% of the liquid per 1,000 foot of depth.
Thank you. One more question is related to slide number 9, or you were about that. It says, what would be the impact of the liquid droplets in the gas phase on the acoustic shock? Is there a certain liquid percentage volume above which attenuation is expected?
You know, in this one right here, there's not enough mist probably to block the shot. In this one over here, there's going to be a liquid level because you're below critical rate. So if there's enough mist to make an interface, you won't see past you won't typically see past the top of the mist. But if the liquid is primarily on the tubing wall, then you can shoot through it. It just so the question is, over here we're liquid loaded. Liquid loaded starts around 10 meters per second, I think. So there's a liquid level in this well, and there's not one here, but there might be mist. And if there's not enough liquid being carried by the gas, you'll see through the center of the tubing and not see level until you get down to the end of the tubing probably. So the amount of liquid's it's important. The more liquid you have, the less on a flowing well, the less likely you're going to be able to see through it because it's going to be gassy liquid all the way to the surface or a mist all the way to the surface.
Okay. And the slide number 27, I think, if a well is flowing below the critical rate, how accurate would be a single shot for calculating a producing bottomhole pressure?
Pretty good. I mean, see the correlation that we developed at the S-curve is good for wells where the gas velocity is below critical. And so when you look at this curve, this curve represents the percent liquid in a liquid loaded well. And so this is in effect the gradient of the liquid based on the gas velocity. This is gas volume over area, which is the gas velocity. So this is the gradient of the liquid when the gas flows at critical rate. Yeah, so it does it and below critical rate. So So this is pretty good. I mean, I've got data where with 4,000 foot of gassy fluid shooting down the casing, shooting down the tubing, the pressures are within 8 psi. I mean, I think it's fairly accurate. Really, I mean, good. Good. It's a good correlation for liquid load gradients.
Okay. And another question, we have a couple more, says, when measuring fluid level in producing gas wells, how soon after shutting the well we need to start shooting the fluid level, and how frequent we need to do the subsequent shots?
You need to have steel-toed tennis shoes on and be really fast. Let me try to explain why I say that. See, here's a well that had, geez, a lot of liquid. That's a gassy fluid column. The tubing went from 7,000, almost 7,500 foot, all the way to 2,000 feet, 5,000 foot of liquid. And it took 50 minutes to get all the liquid out. The other well I have in the paper, it took 20 minutes. This well flowing above critical, this well, right, where's it at, right? This well, it took about 20 minutes. See that, look, right here. There's 5, 10, 15, 20, 25, 30. In 30 minutes, it was out. All the mist was out of the tubing, and the conditions were completely different than the first shot, which the fluid level, the mist level was at the surface. So in this well, in 30 minutes, the fluid level, which was just mist, went from the top of the well to the bottom of the well in 30 minutes. So if you're not ready to shoot the fluid level, when you close the well off to shoot the fluid level, the gradient that you get about 15 foot change per psi if it's liquid loaded. If it's oil, and about 10 feet per psi change if it's water. So if the pressure builds up 10 psi, it's moved. The liquid will move 100 feet. So I mean, if you've got a really gassy well, it's building up 15 psi per minute, and you wait 10 minutes. That's 150 psi. That's 1,500 feet. That's a lot. It's going to move a lot. So you got to be ready to go when you close the valve if you want to get the normal representative conditions in the well when it's liquid loaded. If you wait and go smoke a cigarette or go do some other kind of work after closing the well in, the fluid level shot may be more clear because the pressure is higher, but the conditions in the well are completely different. And that's important to remember.
And a comment to add on that is, I remember, probably 2008, 2009, on the north of Mexico, they have a lot of gas wells. I was to work in a company, and they shut in the well, and they were not shooting. I said, why you don't start shooting? I said, no, because the first shots we don't see anything, and then started shooting like 15 minutes later, and the fluid level was almost out of the tube. I said, no, you need to start earlier, even though you don't know when you're going to start seeing the liquid level top.
Yeah, you're exactly right. That's a common problem. I mean, people in the Utica Shale were doing that. People in South Texas. I mean, every place I've gone, when people shooting fluid levels, tend to try to close the well in for a period of time to make it easier to shoot the well, and then they don't understand why it doesn't make any sense.
Yes, that also happened with a different company, same North of Mexico, and they knew we were going to shoot some fluid levels, so the operator, for some reason, thought it was a good idea to go and shut in the wells, and then we went like 2 hours later, no fluid in the well. Of course, there was static shots.
Yeah. So the conclusion is, if you get all these shots that there's no liquid in the tubing, these wells are just bad wells. They're not liquid loaded, and so if you shut the well in and you hide the liquid that's in the tubing, then you're going to misanalyze the well.
Right. And we have one more question from Handy. I think it's the last question so far. It says, for a gas well with packer, does a deep liquid level in casing can be a sign of a tubing casing communication?
Well, it depends. If the casing was filled with liquid, and which is common for a gas well with packer, they fill it with treated liquid, treated water, and you shoot the casing and you have a fluid level down deep, then either the packer's leaking, there's a hole in the casing, or maybe you got a hole in the tubing. So usually if it's a hole in the tubing or a hole in the casing usually will add water, and the tubing usually will leak out water. So if you have a hole in the tubing with a packer, usually the liquid level is going to be down near the hole in the tubing, and the water will have leaked out. But if it's a casing leak and it's coming in from the casing, usually, not always, the casing will add water and maintain a high fluid level. So it's either a packer leak or a hole in the tubing, probably.
Yeah, he could also check on pressures. That probably tell him more.
Yeah, pressures can tell. You know, if you shoot the fluid level and the pressure at the packer down the tubing shot and the pressure to the liquid are equal at the packer, then it's likely the leak is at the packer. So you can shoot down the tubing, shoot down the casing. If you have a fluid level in the casing, and if the pressure at the packer is equal, then it's probably a packer leak. But if the pressure at the liquid level is equal on the tubing and casing shot, then it's probably a hole in the tubing.
Yeah, no question. Well, that was the last question, and I think you have some examples to cover, right?
Yes.
Okay, go ahead.
All right. So what I'm going to do next is I'm going to go into TAM here. I think I've got TAM loaded. Well, it didn't pop up, so I'll go here. All right, so this is from last week, and we talked about this equivalent gas repump fillage line. And if I go pick a well, then the data was stored in this folder, the 6th presentation. And if I scroll down and you've installed it on your computer, then it's going to be called LL for liquid level gas wells 2020 presentation number 7. And we've got about 6 wells here to talk about. And so let me just talk about the different examples that we have, and I'll open this. We'll open this one first here probably. And so this is a well that was up in Wyoming, and let me go to the first shot. Let me go back here to the first shot. Now I usually click on the tabs, but you can also go click on liquid level history, and click on a particular shot. Like here's a casing one. If I click right there, it'll go to the casing shot. So this is probably easier than going and using the tabs, but I just have a habit of not using the liquid history, which is probably a better technique, much more productive, but I usually just click on the tabs. So here's the first shot on this. This is a gas well that's liquid loaded. It's below critical rate, and this is a shot down the tubing, and the gas gun shows the tubing. And first thing that you probably wonder is why is there more condensate than water, even though the liquid volumes are the same? And that's because that we rounded off to the nearest whole barrel. And if we go click on edit and bring up the edit screen, we see that there's 1.2 barrels of oil, which means more height of the condensate and less water. It's 80, it's like 40% water and 60% condensate. And we draw that based on the well test. So anytime you shoot a fluid level down the tubing on a gas well, we're going to show the fluid in the tubing divided based on the fluid volumes from the test. And you'll have needed to have typed in the oil API gravity and the water gravity to get the weight of this fluid be calculated properly. Another thing we might want to look at on this well is on the mechanical wellbore. This is pretty old data, and all I have is the end of tubing. I don't have any other kind of fixtures here, so that's just the depth of the tubing. It was a flowing gas well. There's no deviation survey. We put the producing interval as the same depth. That's what often happened in TAM and TWM in the past. So if we had a recent wellbore schematic on this well, or wellbore schematic, I'd re-enter the whole wellbore, but I don't have that information. Anyway, that's the well data. I just want to show you the oil and water percent. Now, when you look, this is shot down the tubing, and it looks like we're using acoustic velocity method. And so if we click on acoustic velocity method, it's saying that It's a 0.79 gas gravity. If I were to count collars, I think I could probably count collars on this shot. And it does a pretty good job counting collars. And you can see collars pretty well here. If I was going to line this up, I'd pick that collar right there. There's a collar, there's a collar, there's a collar, there's a collar, 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 collar. So I can see the collars. And these aren't collars. These are the tubing collar recesses. And so there's that one, and it says a 0.67 gas gravity. So I'm not sure why we use a 0.79 gas gravity, but this one is showing on the first shots, the first shot of 0.67 gas gravity. So it doesn't count very deep because the tubing collar recesses are hard to see. But anyway, we could see that. This well, if you go look at the report, we can see that this is the same report I showed in the presentation to show the well in liquid loaded form. And this well has that deliquification report. And if we scroll down toward the bottom, if you shoot down the tubing on a liquid loaded gas well, that deliquification button appears. And I don't remember tubing size, but you can go in and select. This is showing 2 7/8 tubing, and I don't remember. Let's see if I can click here on edit. Okay, the tubing is 2 3/8, so really the critical rate is less than that. So if I click on modify, I can go change it to 2 3/8 tubing, which is right here, and then save that. And now the critical rate is 650 MCF per day. You can adjust it. You can select Turner or I think Coleman if you want. This is just shooting down the tubing, and all we did here was, if you look at this liquid level history report, you can see we did this test over time, and here's the 332 test, and then we shot up the level about every 14 minutes or so, and we depressed. Well, here's a casing shot we took, and then there's some more tubing shots. We depressed the fluid down the tubing, and the round trip travel time got longer and longer as the pressure built up, and you can see I don't see the tubing pressure here, but we have tubing pressure. Let's click on select columns and add the tubing pressure here, tubing pressure, and the tubing pressure gradually built up from 357 to 54, 454, almost 100 psi, and that occurred over a time of an hour. So in an hour, the pressure built up 100 psi, and it pushed liquid level down almost 8,000 feet. So that's again, that you shouldn't take very long on shooting the flow level. I would probably, if I had to reanalyze this, I'd go to the next shot and see what let me scale it down here. It's kind of collars down to here, and acoustic velocity is 1263 here. The acoustic velocity is 1267. That's matching pretty well. So I'm okay with that. We're just pushing the fluid level down as the pressure builds up, and we're actually measuring the change in pressure versus depth. And if it plots as a straight line, then it's probably a good gradient that we would use to estimate the gradient of the gaseous fluid column. All right, let's look at another well. And now this is a well that we were treating with surfactant down the casing. And let me go to the first well here. And the first shot was down the casing, and you can see that there's an upkick at the top perf. Now, there's a top perf, and you can also see the end of tubing here, but you can't see the bottom perf. That upkicks into tubing, and that upkick right there is top perf. I can't say always, but almost always when you shoot a gas well, if the top perf's uncovered, you usually get an upkick at it, and it's usually a great marker. So here we're using the top, we're using the end of tubing as a marker. We would, and the distance to liquid is 60, 67. If we go back to downhole marker and we use the top perf, the top perf right there, it's distance the same depth. And so in this well, it's not, the temperature is probably the same, pressure is about the same. And so either the top perf or the end of tubing give you exactly the same distance to liquid. So that's sometimes you get, when you have a hot well, the perforation, you want to get the perforation right next to liquid level as deep as you can, because the temperature has a much larger impact on the acoustic velocity than this well had. The other shot that surprised us was when we shot down the tubing, and this is probably the tubing shot right here. I think we're shooting with the 5,000-pound gas gun, and this kick right here is because when we fired the shot, well, this looks like a remote fire gas gun maybe, but anyway, this double kick here is probably from the way we rotated the valve on the remote fire on the 5,000-pound gas gun, and that we'll probably need to talk about that later in another video. But you need to make a nice smooth motion when you fire the remote fire gas gun, the 5,000-pound gas gun, not the remote fire gas gun. The 5,000-pound gas gun, you have to rotate the handle 180 degrees and not shake it or pause as you rotate the handle, and then take your hands off the gun so you don't shake it. So I don't know what this is caused by, but that's probably a manual. We probably made the shot look like that by the way we fired it. But that shot down the tubing, and look, it looks like we're doing it in both cases. So these are shots down the tubing, and the fluid level is pretty high. It's mist. It's soapy. It's soap. And so when the software calculates a gradient here, not soap, but it's soap bubbles, it's really light. And so the software assumes that it's much heavier because the pressure buildup's not very fast. It's not a high pressure buildup. And so the percent liquid, if we go to the report, we see that the percent liquid is 24%, and this pressure here is a lot of this liquid. And so why is that important? It's important because you have to be cautious when you shoot down tubing and you've treated it well with surfactant or soap, because it's going to lighten the gradient of the fluid a lot lighter than what we calculate. You need to be aware of that. So if you're dropping soap sticks, always shoot a fluid level before you drop a soap stick, so you get more normal representative behavior of the liquid level. And then after you drop the soap stick, you'll see it typically fizz up and raise the liquid level and maybe even flow. And that's because it reduces the gradient. It makes it lightens the gradient, and it reduces the surface tension. Okay, that's a well. And then the next well is this is a gas storage well. And I like this. This is a good example because what it shows us this really unusual echo. And if we look at this echo, and Ken has seen these all, he's gone even to offshore Australia and seen the same kind of echo like this. And so we're going to go to fine tune and apply the low pass filter, and see this looks like collars kind of. And so you're wondering, why is it looking like that? And you're thinking, well, I can't see a liquid level. So you turn on the low pass filter, and it takes all that noise away, and there's the liquid level, and that's incorrect. And so this is the fluid level down through the casing annulus through liquid. And if we go to acoustic velocity method and change the acoustic velocity to 4,300, around that, it's not exactly that, but that's close to that, then the down kick is right there at the packer. And so this is an example. We shot through the liquid, and this is a down kick at the packer, and you don't think it's that because you think it's a high fluid level. So if you see a down, which is the packer, and then you see an up, which is an inverted echo of the packer because there's a little bit of gas at the surface, 15 foot of gas at the surface, and then a down, and then an up. It's not a hole. That's the inverted signal echo of the packer. And so down, up means you shot through liquid on a well that has a blockage at the bottom, a packer. Now, if we go back here and we turn the low pass filter off, let me go back to counting collars, and That's not even correct. The gas is probably a 0.6 gas gravity, 0.6, probably 0.6. So I'm going to go in here and I'm going to type in a 0.6 gas gravity and make it to be 0.6, and that's actually the composition of the gas. It's a 0.61 gas gravity with about less than 1% CO2 and 1.8% nitrogen. So that's actually the gas in this well. And so we're going to use the gas acoustic velocity because we can't count collars. And if we turn off the low pass filter, okay, now I'm going to take this little dot, see this little dot right here? And when I start to slide it to the left, notice how we're getting less and less depth. And I'm going to slide it, first of all, I'm going to take the liquid level and slide it all the way to the surface, or pretty close. And then I'm going to take and continue to slide this over here until I get to the point where I'm almost at the surface, and I'm going to pull this over too. And then I'm going to scale this down. What I want you to see now is I want you to see that, look, the time from here to here, and from here to here, and here to here, here to here, and here to here, that's the echo off the top of the liquid in the well. So right there is the liquid level, and it's 15 feet down. So this is a well that has liquid level 15 feet from the surface in the casing that was KCl water, and when we shot it, we misinterpreted the data, and we said it was down about wherever that other fluid level was, and that was not correct. And so you'll see this on offshore wells where they have the casing annulus filled with kill fluid. You'll see it. You'll go to an offshore well on a platform and they say shoot this well because it has some casing pressure on the annulus, and don't bleed the pressure off before you shoot it. Shoot the fluid level, but get the grease out of the valve if there's grease in the valve. But anyway, shoot it and see the liquid level. If you bleed the pressure off, the fluid level will come up to the surface and you won't see anything again. So this is we learned a lot. Ken and I learned a lot on this well. It's a very interesting well. We've seen this all over. This is easy to misinterpret. And so when you see this, well, you can't see it now, but if I turn on the low pass filter, when you see that, I clicked the wrong button. When you see this down and then an up kick, and they're equally spaced, this is the same time from here to there and from there to there, then it's probably shooting through liquid. And normally a hole will kick up first and then repeat down. So people sometimes think it's a hole, but it's not. This is really a good example on this kind of a problem. Okay, got about 10 more minutes. Let me go pick another well. We didn't have any production data in this well because there wasn't any water being produced. But we probably should put one water, so this would be calculated based on water and not calculated based on oil. So if I was going to calculate the pressure at the packer, I'd put a 0 here and a 1 here. Okay, and I would type in the gravity of the KCl water, 1.17, and then when I save this, it's going to change this to be blue, and then the pressure here is going to be calculated correctly. But if it shows the color here is gray, that means it's using the oil gravity, and that would have been an incorrect calculation. So whenever you see the color that doesn't match what you think, like blue's water, gray is oil, and in this case, this was all water. It's all KCl water, and so now when we look at this this fluid level shot, when we go look at the report on this shot, it's going to have a very high pressure right here at the packer in the tubing, and it's going to say 3,240 psi. So that would be the pressure that you'd expect to see right there inside the tubing if you shot down the tubing around 3,200 psi if the packer is the leak. And so if we go look for a tubing shot, let me see if I can find that real quick here. Click here and go to tubing right here, and close this out. You can see right there, it's into tubing. I don't know if Looks like we picked the top perf, but I would probably say that's the end of tubing. And so if we look at that pressure here, and it should be around 3,200 psi. Let's go to the report. The report says the pressure right there is 28. So it's a little less than that. You know, the pressure. So maybe the pressure is not the packer, and maybe not. I'm not sure why there was pressure leaking in, because the pressure at the packer is going to be less than the pressure down the tubing if it's filled with water. With that high gravity, I don't know if it's 1.17 or not. All right, so that was this well. Then the next well we're going to pick is we've already talked about these two in a previous presentation, so I'm going to skip this one, and I'm going to talk about the hole in the tubing at 4325. And there's a couple examples of fluid shots and holes in tubing. Now, if you look at the liquid level history, you can see that we shot down the tubing at the end. This is at the end. And we shot down the casing at the beginning. And the casing pressure increased about 14 psi, and that pushed the liquid level down. So what I want you to notice when we go to the fluid level shots, if we go look at the fluid level shots here and look at the very first fluid level shot, which is right here, I just clicked on the first line right here to go to the first shot. Notice this is down the casing, and there's a lot of liquid above the end of the tubing. And so if you go out to a gas well and there's no packer in the well, and you shoot down the casing, you should believe with all your soul that the liquid level is supposed to be right there. And so every time you come to the gas well, if there's no packer and the casing valve's closed, the liquid level is going to be right there, always. And when it's not, you got to figure out why. And that's an important step in troubleshooting a gas well, because this fluid level, it can't be up here. It can't be up there because the gas can't flow into here and make it come up. The gas is going to come into here and push it out. And so it's not always, but right now it shouldn't be here. That's a problem. I'm troubleshooting the well and saying this is a problem. You got to figure out what's wrong here. This fluid level is high. Figure that out. All right. So we see this high fluid level, and we go to the next shot. It's at 6730, and the pressure here is 125. The pressure here is still the same pressure. I go to the next one. The pressure is 127, and now it's going down 6795 versus it's gone down 2 joints in just a short amount of pressure, just 2 psi. And then some more pressure, and it goes down farther. And some more pressure. See, it's going down farther and farther as the pressure builds up. I think that's a tubing shot. Okay, now here's the casing pressure shot, casing shot. If I turn this off, and okay, let me talk about this real quick. This is an annotation that I put on the screen here to show a note. And so if you right click on the screen, it gives you some options, and one of them is to add a note. And so I clicked on the screen and I right clicked on it. I right clicked on the screen and I put this note here and said hole in the casing shot's black and the tubing shot's blue. And so that's a note. If I go back over here to annotations, I have used a previous shot and it's highlighted in blue. And so this shot right here down the tubing is a shot that's being displayed in blue, and they both show an upkick at the exact same depth, not the same time. Okay? Now, if you pick time, then they may not match up because the acoustic velocity could be different in the tubing versus the casing, because the gas could be slightly different. The gas in the casing may be drier. The gas in the tubing may be a little bit wetter. All right, so this is a great example of using the overlay feature to compare the 2 shots that show the problem is in the casing and upkick, and the problem is in the tubing and upkick, and this indicates there's a hole of communication through the tubing. We added a note, and then you can put this in a word report, and send it off to your boss along with the report, and that would tell you pretty much everything you wanted to see. The report just puts a note. See, the report puts a note right there, and the note is on the next page, and so it's not. I think that copying, and so see, there's a note. That's what that is. And if we were to right-click on this, there's different ways you can use the clipper right here at the bottom to clip this out and put it in a report, or you can right-click on it and paste it, copy the image to a clipboard and paste it. So I would want to send this analysis along with the PDF report and include that as part of my report. Carrie Ann, I think it's about out of time, and you're welcome to wrap this up.
All right. Well, thank you guys so much. Thanks, Lynn and Gustavo, for the question and answer session too. We appreciate your feedback. We appreciate your comments. We always appreciate you joining us on our Wednesday sessions. It's always a pleasure seeing all of you and hearing from you. So if you have any follow-up questions, please let us know. But we appreciate your time today, and we're glad you've joined us. And we look forward to seeing you next Wednesday.
Yeah,
thank you so much.
Thank you very much.